happy to introduce Mr. Rolf, Dr. Rolf. Dr. Rolf is currently a postdoc at the Harvard Data Science Initiative and is an incoming faculty to the computer science department here. And why this is so exciting is because we have a whole lot of overlap between her interests and our interests. We really want to develop a relationship where we can be writing grant proposals together, doing research together, helping build each other up. And so my hope is that we all get to see her amazing work today. That all inspires us to have some more conversations on how we can just sort of continue this relationship as she starts to move to Boulder and starts to build her career that is really synergistic with all the things that we do. So please give me a round of applause and welcome Dr. Esther Rolf.
Thanks, everybody. Thanks, Kai, for the intro. I have a lot to cover today, so I'm hoping to get through everything. If you have kind of high-level questions, I'd ask to keep those to the end, but definitely if you have any comprehension or clarifying questions, just like raise your hand or shout out because everyone will be following this website. Great. So this talk will kind of give an overview of the part of my research that focuses on geospatial machine learning. So I am in the computer science department, coming to Boulder in August and very excited about that. And my core research is in machine learning, and the way that I look at geospatial machine learning really focuses around the characteristics of geospatial data and how that's different from a lot of other machine learning data, and how that can influence the way we design, develop, and evaluate our machine learning algorithms. I like to start with this quote, sometimes for machine learning audiences, but I think everyone here will probably feel similarly to the United Nations Global Issues quote here: data is the lifeblood of decision-making and the raw material for accountability. It's new sources of data, such as satellite data, new technologies, and new analytical approaches, if applied responsibly, that can enable more agile, efficient, and evidence-based decision-making, and can better measure progress on the SDGs in a way that is both inclusive and fair. There's a lot of goals here. There's some technical, there's some social, and there's a lot of potential and a lot of promise. As a machine learning researcher from the computer science side, I take that quote, and this is what I see. We have a lot of vast and varied data about our world. We have satellite data, citizen science data, mobile phone data, census records, and so many more. And within each of these categories, there's so many nuances to what data looks like. At the same time, there's pressing environmental and ecological and social phenomena that we have data gaps that we need to address in order to address global challenges. So in two examples that I am currently working on now, so there won't be a lot in the slides, but talk to me if you're interested, that would include things like mapping tree canopy height in local regions or detecting artisanal metal mining to understand where that's occurring and hopefully connect that to potential health outcomes. But in between the raw data and the information sits a pivotal question, and the promise is that machine learning can help us translate this data into information that we can use to fill in these gaps. But when you look at it from the machine learning side, it's not always so easy as just inject neural network in the middle of this data and you're good to go, right? There are a lot of key technical distinctions of geospatial data that come into play for machine learning researchers and how we design, develop, and evaluate our models. And today I'm going to talk about three of those. The first is just the sheer volume of data that we have around the globe, which can come at a challenge to actually making these algorithms and models that we're developing accessible to the wider research and global community. The second of these is just the structure of the data. We have a lot of spatiotemporal autocorrelations. I'm sure everyone in this room is familiar with that. It's literally on the whiteboard over there. But for machine learning, this can actually break some of our assumptions and make things more challenging than anticipated. And lastly, I'll talk about the promise in heterogeneous data sources as an opportunity for machine learning to actually step up and model these different forms of data. So these will be the three main kind of elements of the talk. And you see that addressing this is actually important. So the machine learning algorithms we develop are actually useful. They need to be accessible. We need to be able to evaluate performance not only on a benchmark isolated data set, but what would performance in the real world look like in a new location or perhaps next year. And we need to integrate all of the data that we have to be making the best models possible. So starting with just scale, I'll orient this part of the talk around satellite data specifically. And satellite data is one of these sources that has this promise to help policymakers and researchers monitor our world and act in it. So it's found use in environmental monitoring, things like detecting forest change over time, in real-time disaster response, finding where damage is worst so that resources can be sent in real time to those locations right after, say, an earthquake or a flood hits. And in the longer range, satellite machine learning models have been used to inform global policy on food security. And in an example we'll return to later in the talk, actually estimating poverty in different regions. At the same time that satellite machine learning has this promise, for many people in the research community outside of the machine learning space, accessing and harnessing the potential of satellite data is actually a technical and computational challenge. You basically need a lot of machine learning expertise. You probably need cloud computing and GPUs. And so my research team on this project that I led during my PhD at UC Berkeley asked if that really needed to be the case. And with that question, we designed MOSAICs, which stands for Multitask Observation Using Satellite Imagery, and kitchen sinks is actually the machine learning method behind it. But the idea is that this system combines satellite and imagery and machine learning for you as the user so that you can predict whatever variable of interest you're interested in, whether that's forest cover, population density, or something else, with ease. And so what does that actually mean? It should be quick. It should be versatile. This will run on the order of minutes on a laptop. And in terms of machine learning expertise, this reduces the problem of needing that kind of heavy duty deep learning expertise to needing basically linear regression and more fundamental statistics. So what's actually going on here in this diagram? MOSAICs, from a user's perspective, takes satellite imagery, converts that into what we call in machine learning a feature representation of those images. And then users downstream have supposedly their georeference labels of something that they're trying to study. In this example, it would be forest cover. And for the regions where that researcher has forest cover, we can do a geospatial merge with the features from the images from that corresponding set of locations. From that, we learn the linear regression weights here. So just really simple linear regression. And then for the places where we don't have those forest cover labels, but we still have the images, we can get the features, run that linear model forward, and make predictions in all of these regions where we didn't have data before. The important thing here is that it's the exact same process and the exact same feature embedding of the images that can be used to predict forest cover or population density or anything else. So you can see how this is now going to parallelize and scale and generalize to multiple different prediction tasks. And all of this is actually enabled by a very simple algorithm by machine learning standards for how we translate the images into these feature vectors. So really quickly, to go into what that featurization process looks like, we're taking one image, and at the end of the process, we're converting that into a d-dimensional featured vector. And so think on the order of like 1 to 4,000. a lot of this is the same fundamental building blocks in a convolutional neural network. It's just extremely simplified. Rather than having a deep network, we have a one layer, very wide, very shallow network where the weights in that network are randomly initialized from the distribution of our training images. So taking a lot of those fundamental concepts in computer vision, but simplifying it greatly, which allows us to have this efficiency. And the truly impactful thing about this method is that once you apply the random convolutional features to get this embedding of the satellite imagery, any user, any researcher with a different set of target variables can attach that to this matrix, solve. This is a ridge regression, so just a linear regression with a penalty on the weights. But all the arrows go toward that final optimization step. And this is what unsupervised learning gives you. Versus standard supervised learning, you also need to optimize over all of the weights in the machine learning model itself. So now if a new person comes and says, all right, well, I want to predict road networks, they need to actually go all the way back to the imagery to retrain the model. But what you get out of something like this is going to be a much more complex, much more expressive model in general, right? So we want to make sure that in the simplifications that we have for mosaics, we're not actually losing a ton of predictive performance at the end of the day. So here you see for 7 different prediction tasks in the US, comparing on the basis of R-squared, so higher is better. Mosaics in green and a fine-tuned ResNet 18, basically the instantiation of that previous slide in blue. And in general, our method is a few R-squared points below the fine-tuned model, right? But if you put this in context of the training times, each bar here took 2 minutes on a laptop for mosaics. Each blue bar took 8 hours on a, at the time, pretty heavy GPU instance on AWS. And that's not even including hyperparameter tuning or anything like that. That's just training this final model. So you see immediately there's a big difference in who's going to be able to even prototype. Will satellite imagery and machine learning help with my problem? And, oh, sorry, I didn't realize this is up here. Just to give some intuition on why satellite data might be separate from other data we're working with in machine learning, why these algorithmic simplifications can work really well for satellite data when they don't necessarily work as well as state-of-the-art models for other data we're working with in machine learning. That's generally, we're thinking about natural imagery. So something you could capture with a handheld camera. So these 2 images up here from the ImageNet data set, which is now very popular in machine learning, they're both the class Red Panda. So in order for a machine learning model to get good performance on ImageNet, it needs to be able to distinguish that both of these images are red pandas, even though one is like the full body red panda and one is squished close up. If we contrast that with satellite images, a lot of the things we're looking for here are actually pretty structurally invariant in images. Houses are about the same size, roads are about the same length, and these structures can help explain why we might not need so deep of a network to capture a lot of these phenomena. I want to show you a little bit what our predictions look like with mosaic. So on this side, you're seeing the ground truth labels of forest cover across the US, our predictions, and then spatially disaggregated scatter plot of the labels versus the predictions. So for forest cover, for population density, and per household income, I'm going to put all 7 of the variables that we're looking at just to show the range of what can be seen with this method. It's hard to see the individual maps, but we see that this common featurization allows us to actually directly compare performance across these different outcomes. So what things are visible from space with a relatively straightforward but emblematic of many other approaches model for machine learning. For the variables that are available globally, we predict globally. So that would be forest cover, nighttime luminosity. So that's from the daytime image, predict the luminosity at night, population density, and elevation is a bit of a weird one to be predicting from satellite imagery, but just to give a range of what can be seen. And the really exciting thing in the last couple of years is not only did we do this research project, but we actually put a big amount of effort into developing a website where users can go and download the already processed feature representations for a global snapshot of the world. So this is built on Planet Labs imagery from 2019, Q3. And from a user side, it's uploading a georeferenced CSV, right? So labels are optional, but we just need latitude, longitude variables. We'll snap those to a grid. Somewhere in a server in Berkeley, it will pull the relevant images and their features, and then it will send a download link, and it'll be ready depending on how much data you ask for in like minutes to hours. And in that effort to actually take the research project and translate that into a usable system, I need to thank a much wider group of collaborators. And we were all really honored earlier last fall to win an award from the United Nations Development Program and the International Telecommunications Union for the potential for this technology to really change the game for who can access, use, and even maybe refute satellite imagery and machine learning technologies. So this is ready, this is available, people are using it. By my account, we have people from many different institutions and many different nations who have logged into the system. And it really is meant to be kind of ready to go. But when we think about what's actually going on here, Mosaics is saying, give me a latitude, longitude, location. I'll query a satellite image from that location. I'll featureize it, and I'll give you that feature. Completely kind of each of these locations is treated as their own separate thing here. And so the next generation for me in this line of work, it's a completely different research team here, but is saying, take this image encoder. Think of mosaics as like the orange part of this diagram, but let's use the fact that these images are distributed over space. And that's the whole idea behind SatClip, which is a contrastive machine learning method, which actually takes this location information into context. So from the machine learning side, the background here is that CLIP is a model that is used for contrastive self-supervised learning that usually takes in natural imagery and then a caption of what that natural imagery is. So it's contrasting an image and the text caption of that image. In contrast, SatClip is using the same fundamental ideas, but we're contrasting satellite imagery with the location of that satellite imagery. So this looks a little complicated, but it's really, I promise, fundamentally not that different actually than the mosaics paradigm. The idea is that across the world, there are all of these different, I'll call them ground conditions that vary over space. And when we actually apply this image encoder like mosaics, we're trying to capture the variation in space that might be due to changes in population density or infrastructure or ecological variables. And what this new contrasted pre-training step does is it says, well, whatever the image encoder was going to give me, that now we're looking at 256 dimensional vectors. Actually, what if we trained a separate model in parallel that only takes in latitude and longitude and tries to basically match what that image encoder vector is? So these two models are trying to join each other in that 256 dimensional representation. But the interesting thing is now, once that training is done, this location encoder alone is helpful. So here we're not predicting anything in particular, but you just see a latent representation of what that model that takes in latitude and longitude and for any location gives you a 256 dimensional vector. What does the actual variation in those vectors over space look like? The research behind this that's supporting this is actually looking at what actual architecture should we learn for this location encoder here. So that's this line of work here. I won't go into it in too much detail, but in case anyone is interested. But let me also talk about how we use this model. So in mosaics, we skip this part altogether, right? We ignore that anything is actually located over space, other than that space is an index by which we get satellite imagery. So we'd usually take the image encoder and then use those features to do our linear regression prediction step. Here, we're actually using the images as an intermediate to learn the location encoder. And then it's that location encoder that we use the representations from to learn this downstream model. And this is really nice because if you give me now a set of locations that wasn't in my training set, I don't have to go query all the imagery. I just have to put those locations through a fixed form model. And so we looked at, in our research paper, a lot of downstream prediction tasks. Here we are predicting different ecoregions with few shot learning. So the prediction model is actually trained mostly outside of Africa, and then it sees a few points from within Africa since ecoregions are continent specific. But you see here are the different colors or different true ecoregions. If you use the embeddings from the location encoder of SatClip, we're fairly similar, especially when you contrast this with one of the few other location encoders that is available right now. The caveat is this one is not actually trained for global, it's not designed for global tasks like ours. And then compared also to mosaics, which would be that direct image encoder, you see that SatClip can actually get the variation over space, but it's a better way to interpolate, whereas mosaics is kind of one image at a time. It's going to be pretty spotty and kind of speckly with its predictions. So to wrap up this first section, when we're thinking about machine learning for satellite imagery or actual use cases, you cannot ignore the volume of satellite data that's available. And so we looked at two different methods to harness the volume of this data, but also at the end of the day, we want the way we package that machine learning component to be easily usable and to be accessible. So mosaics did this by pre-computing all of those image embeddings once, so that any researcher or team who might want to use this doesn't have to recompute that computation. It's stored once and ready to go. And SatClip does this a little differently by looking at what information we can extract into a pretty small location encoder. So volume is one piece of the puzzle, right? Sheer size brings its complications, but there are also facets of geospatial data that the machine learning community is starting to deal with, has been dealing with for a long time, but are really fundamental to these types of predictions. And I'm going to talk about those in the context of real world performance and what it means to achieve fair predictions or to be aware of spatiotemporal autocorrelations in our errors. So I'll briefly go through this because probably everyone in the room kind of knows what I'm talking about. But we're thinking of Tobler's first law of geography. Everything is related to everything else, but nearby things are more related. So in the context of house prices, house prices are very neighborhood effect dependent, right? If you know what your neighbor just sold their house for, you know kind of a good estimate of what you could put your house on the market for. If you're an equation person, this is spatial autocorrelation. If you're a picture person, that's spatial autocorrelation. Generally, we expect the correlation of nearby points to be closer than for farther away points. But what does this mean for machine learning? And especially in contexts like the satellite image and machine learning motivation from the very beginning of the slide, very often we're dealing with underlying values like amount of tree cover or poverty that have high spatial autocorrelation. But we're dealing with data, our training and evaluation data coming from sparsely clustered samples. And this is because it's so expensive often to collect that data on the ground. But what happens when we have these sampled sites and we take a standard machine learning approach to splitting a training and evaluation set, which is take 80% of these dots uniform at random and put them in a training set, and take the other 20% and put them in a test set. Any thoughts on what might happen there? Great, I'll answer. Oh yeah, go ahead.
Training set might take entire clumps that are part of the geospatially, like entire geospatial clump might be part of your training set and not your, and you don't have any of it left over for your evaluation set if it's a small sample like that.
Yeah, that's an important point. And also kind of the reverse. So you might use this point as your evaluation point, and you've seen everything around it during training. But what if you need that model to work here? You don't have any training data near that. So the thing we're kind of most fundamentally worried about here is that taking this standard IID test split from a fixed spatially biased sample like this can generally overestimate model accuracy. So to show you what I mean, this is again those 7 prediction tasks that we use mosaics for. The dots are the bars that I showed you earlier. Those are basically taking this uniform at random held out split, because that's what's conventional in machine learning. But what if we actually spatially block our training and validation data? So this is delta is the width of these cells. You can see as we go from 0.5 to 16 degrees, the learning problem is getting a lot harder, right? Because everything in our test set is actually much farther from things we've seen in our training set. And as a result, for some of these variables, performance goes down quite a bit compared to what we would have concluded if we had just done the standard machine learning thing, declared success, and walked away. And so this is one example of how we might parameterize spatially aware cross-validation. So that was an example of block cross-validation. People also do buffered cross-validation. There's a whole set of options in this space, many of them actually coming from the ecology community. It's worth noting also that for the machine learning folks, this is step 1. Like if you don't know about spatial cross-validation and you're making spatial predictions, you need to know about it. But that's not really where the story ends, because we're not just trying to assess, can my model perform outside of the training set at all? We're often trying to get an assessment of what is our estimated accuracy over this entire region. And for that, spatial cross-val won't actually help you. You need to collect really good evaluation data. So this is something that the ecology community has been in dialogue about, and I'm trying to bring that back into the machine learning community so that we're orienting our evaluations of performance toward actual real world use cases. Apart from just evaluating performance, part of the reason we would want to evaluate performance is to compare different models that we might use. And actually, location is a really interesting type of data to put into a machine learning model. So I want to pose another question to you all. Let's say we want to make a model to predict housing price from factors like number of bedrooms, square footage, when the house was built. And somehow we only have data from the northern half of the US, and we need to predict in the southern half of the US. Think of this as like a simulated example of training in one country, testing in another, something like that. So my question to you is, I'm going to train a neural network or a random forest model or some kind of linear model to take in all these input features, predict housing price, but only from data up here, and then I'm just going to apply it to southern half. So in addition to things like number of bedrooms, year the house was built, should I input latitude and longitude as data for that model? Raise your hand if you think yes. No?
Yeah.
Not sure? Okay, great. Folks were mostly on board here in that if you had said yes, which no one was brave enough to raise their hand and do, because I think I set it up pretty well for you all. If you said yes, you would train your model in the north, and you'd be really happy with its performance, right? But when you go to the south, it would just be catastrophically bad. On the other hand, if you ignore spatial information altogether in your model, you have a much lower performance in the north compared to the gray bar, but your drop in going to the south is much less. There's still a shift in the distribution there, so performance is going to go down, but much less. And for those of you that were kind of like hesitant or wishy-washy, maybe you had this intuition that, yeah, as a direct input, this might not be good, but it still carries a lot of information. The fact that there are neighborhood effects, that structure is consistent in the north and south. And so that's what this yellow bar is going towards. It says, yes, this data is important. It tells us about the structure, but don't necessarily use it as a direct input feature. And so from that, you get a little boost in performance in the north, actually a tiny boost in performance in the south. But what I would say there is what you're really getting in the south is not degraded performance, but you're still using location. And this is actually using a very simple post-estimation smoothing method that I developed. But the idea is that that structure is there in the data. We need to be more careful and more intentional about how we encode that in machine learning models. The third point I want to make that people might not realize from many different communities is what happens to our predictive performance and error structures when our underlying data has these spatiotemporal autocorrelations. So to look at this point, we're going to look at actually a specific case study that I did with some of my collaborators. So Emily Aiken and Josh Blumenstock work in kind of the machine learning meets development economics space. And they actually develop maps for predicting poverty that get used in collaboration with different governments. So we looked at a really simplified version of what their pipeline might look like. We're taking the mosaics features from earlier, matching those to government surveys, and then taking some of that data as the evaluation data for our satellite-based predictions of poverty. And what we're going to do is say, well, if we just took these predictions out of the box, and then we used those predictions for some very heavily simulated policy, which says, take the 20% of regions that have the lowest predicted poverty. For those regions, we're going to grant some kind of allocational aid. So like on the order of stimulus checks after COVID in the US. But since in many nations, there's not actually census records, let alone tax returns from the previous years, how do you send that information out? And so selecting the 20% of regions with our lowest predicted scores is our simulated way of getting at what might happen in practice. But what might actually go on here? So one of the really important factors in this is thinking about predictive performance over a country, but distinctly in urban places in that country and rural places in that country. So here we're looking at 10 different countries where we've trained country-specific mosaics models, and then we're evaluating the performance just of our predictions of wealth. And if we evaluate as a country as a whole, we actually get pretty good performance. Spearman-Rowe is a rank correlation coefficient. So we're basically sorting different regions pretty well across the entire nation. But if we look at just rural or just urban places within those countries, our performance drops off quite a bit. And the underlying statistical reason for this is that in most of these countries, rural places tend to be poorer and urban places tend to be wealthier. And so a model that can distinguish between urban and rural places can actually distinguish between a lot of the variation in wealth. And that's what you're seeing in the gray bars. But when policies are actually rolled out as to who gets aid, often different policies are enacted in urban and rural places. So we're actually often in this case where it's the red and the blue performance that matters. And we see that if we look at this simulated targeting program, and we say if we selected 20% of the regions according to our predictions, how would we do? On average, we do worse when the policy is only rolled out in urban or rural regions. And this is perhaps not incredibly surprising, but again, what are the common ways of evaluating these models? Apart from our work and the paper referenced here, a lot of people are just showing the gray lines and declaring success when what I'm seeing here is we need to actually hit on performance specifically for certain regions. And just to give some intuition again for why this is happening, because mosaics is this feed forward representation, and this is actually just a fixed embedding that we pulled from our own API. We can look at what those representations of images look like across urban and rural lines. So for every location in our data set, we've given it a binary indicator of whether that is an urban or rural location. Again, like not perfect, but binarizing gets us at least able to see what's going on here. We take again a low dimensional embedding of this high dimensional feature space. And so every point that you see on here is one image in this two-dimensional feature space, colored by whether that image is a location that is urban or rural. And so you can see that already in a lot of these places, we can separate urban and rural places in a two-dimensional embedding, which means we can predict that binary indicator of urban or rural pretty well with these image embeddings. Okay, and the reason we're getting some of this phenomena in our error structures is because we can predict urban and rural, the difference between those pretty well, and because that difference tells us a lot about the mean difference in wealth for urban and rural places. A lot of what we're picking up on in our representations of satellite imagery when it comes to predicting wealth can be explained by a model that just predicts urbanization or level of infrastructure. And so that then changes the types of errors or concerns of unfairness that we're looking at. If you are looking at predicting poverty in an urban area in many parts of the world, your satellite model may correctly identify that that place is urban, that has a lot of infrastructure, but it may incorrectly apply the correlation that urban places tend to be wealthier. So our risk is fundamentally and systematically missing poorer pockets of urban areas in parts of the world. It's also not that easy again, because generally, based on the correlation that more rural places will tend to be less wealthy, just basic statistical reversion to the mean will, in general, lift those predictions up. And so you have these counteracting phenomena that we look at in this paper. We look at it specifically for poverty mapping because this is a case where it's actually being used, and the disparities in allocation are very tangible and understandable. But this idea that we very definitely have structures in our errors from geospatial models is one that I think deserves a lot of attention, and probably a lot of people in this room have a lot to add to this. But that kind of concludes this second part of what makes data from geospatial sources unique for satellite imagery. It challenges a lot of our normal paradigms for model evaluation, and it introduces these questions of spatially correlated errors that can really hinder the actual use of these predicted maps out of the box. So lastly, and this is kind of the most forward-looking section in what I think of as a big opportunity for machine learning, is in the heterogeneity of the different data sources that we have when we're looking at actually trying to get this comprehensive, data-driven, fair picture of what's going on in the world that UN quote from the very beginning hopefully motivated us for. And in really simple terms, what does this mean? It means when you're actually making a machine learning model because you need to fill an information gap, you want to use all of the data at your disposal, right? So this is kind of too small to see, but this is more along the lines of what the actual poverty mapping systems look like. We use mosaics because it was simple and easy to retrain, but they're using a ton of different data sources, including phone records, to get a more comprehensive picture when they're actually using those models in practice. And in the 2 projects that I'm working on now, this ends up being important. We're fusing satellite data with drone imagery, with on-the-ground samples and health surveys. And all of those data have their own specific forms and structures. And right now, each of these projects really thinks one-off about how that data can be integrated. But I think there's a real opportunity in thinking about general methods that can ingest different forms of data. So to give you a picture of what that might look like and how machine learning frameworks might need to change there, this is an example where we were trying to, at the end of the day, get really high-res land cover predictions across the US. We have 1 meter resolution imagery from NAPE, and then we were also using a bunch of different data sources for what land cover might look like, but all of them imperfect, none of them at 1 meter resolution to match the imagery. We have 30-meter resolution land cover data from USGS, and then we have, for some classes like roads and waterways, really high-res vector data from OpenStreetMaps. And so what these gives us is kind of a sense of what the land cover in each pixel might be. But just because this pixel says the average in the 30 by 30 meter square is field, this bright yellow class, that doesn't actually mean that this pixel here within that 30 by 30 is going to be land cover. So we need the imagery to kind of resolve the uncertainty in these underlying data. And in this work, we actually develop a new framework to deal with this type of data based on a Bayesian approach where we're saying, take the data we have, actually allow it to be uncertain. Don't treat it as the ground truth label for each pixel. Treat it as a probabilistic prior for what might be in that pixel. And so just like in Bayesian inference, we then have our observations from the 1 meter satellite imagery, and those help us get this posterior prediction over what each 1 meter pixel land cover prediction would be. So this is the loss function we're using. Unlike most generative modeling, this actually can be used as a standard loss function. It's like 3 lines in PyTorch. It's very simple to implement. But a really interesting thing about what you get out of this modeling framework in general is most discriminative models, most standard machine learning models would just give you a prediction of every pixel in the image. And you'd convert that to, okay, this is the most likely class. I think that this pixel is one type of wetland or the other. And so that's what you're seeing with these light and dark blues here. Our model actually does something a little bit different. It gives you outputs that are highly certain in regions where the prior and the imagery can agree. And then there are some classes, like these 2 types of wetland, that the model actually has a really hard time distinguishing between because we have a very small model for our imagery model. So it can't actually tell you the difference between the 2 types of wetland. So it basically doesn't, right? It falls back on the prior belief and says, I can't tell you anything substantively different from what your prior has. So this is an example of a way that we might think about not just these 2 data sources, but using other types of data, other modalities of data, and putting that into not a raster file of what we think the true ground conditions are, but a raster file that tells us maybe how uncertain we are in different places. Maybe our prior is actually very, very certain because people don't really label roads in OpenStreetMaps if there aren't roads there. That's, if you get a road in OpenStreetMaps, almost certainly there is actually a road in that location. You can be very certain about those things. Whereas some of these rivers are super seasonal and some don't show up for a whole year at all. So maybe those are then less certain in that corresponding prior. But what are the kind of design questions for the next thing that you might want to model? This is a way to, as long as you can specify how your data sources contribute into this week prior, then this framework of machine learning can apply. And zooming back out, the whole premise that I've been talking about, right, is that geospatial data is different for machine learning. And not just for the way that we design our models, but for the way that we evaluate them. A lot of this talks specifically about satellite data because I work a lot with satellite data, but a lot of it is also more fundamentally a geospatial data question. When it comes to satellite data in particular, the approach from machine learning often is one of taking machine learning methods that were designed for usually natural imagery. So think back to the red pandas, taking these model architectures that were designed for this regime, lifting them and shifting them over to satellite data applications, right? And so my research and what we've been talking about today actually says we can do a lot better. We can make models more accurate, more efficient, more interpretable even if we focus on this as a distinct research agenda. And that's exactly what this paper covers. This is developed and co-led with my collaborator, Hannah Kerner at ASU. And this is a paper that is trying to speak to the machine learning community about why is satellite data different than you think of a traditional image modality for machine learning? Why do we think about this as actually its own distinct modality for machine learning? I'll kind of briefly go through the arguments that we present in this paper. We have different spatial resolutions, different time steps of data, different modalities of data, this rich and varied distinctions in how we can sample satellite data that make it really distinct from natural imagery, which is right now the common focus of machine learning development. And as a result of how this data looks different, when we're thinking about an instance, we're not thinking of like red panda image, caption red panda, right? We're thinking about, I have a location in space I care about. I have tons of satellite products that I can use to describe this space. And I may or may not have good labeled data from that location. This is, again, like a fundamental shift a little bit for machine learning. We need to specialize our learning strategies, our model architectures, and the way that we incorporate domain context or allow data to be something different than a ground truth label, but maybe an uncertain notion of how things might change over space. We talked about already the need for specialized evaluation. And I think possibly interesting to many people in this room is the way that this geospatial modeling comes back to machine learning as a kind of core discipline. And that's because these questions of learning from multiple modalities, these questions of training a model in one location or one distribution, and then needing to shift to another during test time, these questions of training with a huge amount of unlabeled data, but then needing that model to work really well with a limited number of ground truth samples, those are fundamental questions in machine learning right now. They are anchored very clearly in geospatial applications. And I think that's an opportunity for these communities to come together. And lastly, this kind of discipline of satellite machine learning is still evolving. And the machine learning part of that community, which I'm in, is a part of it, right? So as we're evolving, we need to develop some guidelines and we need to develop the privacy, ethical, environmental impact aspects of this work. We need to make sure that perspectives from many different communities are in on that conversation and that we are constantly evolving our research goals and actually the models that we produce and put out there. And all of that is to say that there is so much to be done. And all of that is in service of this idea that fundamentally this data can enable so much progress if we can harness it. And so that's going to take many different scientific communities, but from the machine learning side, we have the opportunity to handle volumes of data so that we can actually prioritize efficient and real world performance. We can harness spatial temporal autocorrelations, and we can learn from multifaceted representations of the world to actually get the best picture possible. And these are the kinds of things that my lab will work on at CU. So from the machine learning side, and yeah, we can talk about any of these things. I'm coming in August of 2024. I'm actually looking for postdocs. So if anyone is in that machine learning space, please reach out. And huge thanks to all of my affiliations and funding sources that made all of this work possible. Yeah, Ty.
I loved where you did the coordinate embedding.
Yeah,
Have you tried it with time embedding also? So we get the feature plus the space plus the time?
great question. So that work is like brand new. And the first pass that we did with that was just over space. Although the Sentinel-2 imagery that is used for the image part of that joint modeling is from a time span of 2 years.
Right.
So the image representation is basically like an average over 2 years, but in the works is the version that takes in latitude, longitude, and time.
Yeah, cool. I had a question about sort of detection.
Yeah,
So in ecology, we think a lot about like, I have a bunny in my yard.
okay.
I see it in the mornings. I don't see it in the afternoon. You know, it's
Yeah.
like you go back and back and back and you see it.
Yeah.
And it particularly comes up with like, it has something gone extinct. How many times do I need to record an absence before I can say this got extinct?
Interesting.
So here it seemed like features were, once they were there, they were there.
Yeah,
And maybe this time embedding gets at it and the Bayesian get at it a little bit.
yeah.
Is there a way that we can start to get embeddings that express some variance in sort of when you would see them, when you wouldn't?
Yeah, I think that's a really interesting question. And part of that, I think the part of this talk that gets closest to that is going to be that Bayesian part here, right? So even here, this is all one time step. But as you were asking, like most of this is only one time step for convenience. It's again a volume question if you want to go back in time and also over space. But you could get embeddings that change over time. And I would argue, actually need to account for the fact that you're never going to see a bunny in this satellite image. So this is a very weak observation if you're looking for bunnies. There you might need a different modality of information. You might need like a yard sensor or something like that. But we need to be critically thinking about, is our labeled data consistent? Is it something that we can totally trust? How many observations before we're pretty certain there's not a bunny anymore? But also, as you point out, we need to think about what is actually represented in these different remote sensing data sources. And so that's actually closer to the poverty mapping example, right? Like, what do you actually see in a satellite image that tells you about a place's relative wealth values? A lot of what you see is infrastructure. And so you might not expect to get a representation that goes much farther beyond that point. I think the question of how you might structurally model that, especially for ecological applications of machine learning, is really, really interesting. Times where you could actually put a more structured model on your data certainty and what you think is represented or not in those features? They're really great question. Really interesting stuff.
Thanks. Well, thank you.
Yeah, yes.
One of the things I'm super curious about, and maybe this can be a longer conversation, like what are the bridges that would connect the environmental science community and the data science community? I'm seeing one big thing, which is training data.
Yeah,
Like, are we just environmental scientists in the era of getting good training data to help bring the data science community to the work that we're doing?
yeah, it's kind of, data is kind of like an if you build it, it will come situation for machine learning. If you have a lot of data and you package that as a challenge or a benchmark data set, I promise you the machine learning people will. The question is whether that's really a two-way bridge.
Yeah.
Right, and whether that is, I'm so glad I made these slides, whether that's this paradigm or this paradigm. And data can definitely get us to the previous one, but I think when we're going here, we need to talk more specifically about not packaging data so that machine learning can use it, but explaining what fundamental structures there are in data that machine learning could adapt and model. And so that's been the focus of my work. I love doing that work, so I'm a little bit biased. But I think that the language that we all speak fundamentally is data. And data scientists or machine learning researchers, we think about data in very structured ways. Ecologists, environmental scientists, climate scientists think about data in very different ways. And I think that's the conversation that opens, is this question around, okay, what do we actually have at our disposal and what might we hope to do with learning?
And what kind of structures are like most interesting right now in the computer science, data science world?
Yeah, so I can tell you what the opportunities in kind of current mainstream machine learning are. So my collaborators and I who wrote this piece, this part of it is trying to say, hey, machine learning community, hey, big conferences like ICML is our summer conference, NeurIPS is our winter conference. Computer science actually usually runs on conferences for machine learning more than journals. What are your big open questions for machine learning? And actually all of those, many of them have a huge satellite component. So all of these are things that get fundamental attention at machine learning conferences. Multimodal learning is often thought about as images and text, not satellite data and proximal sensors. Distribution shift is usually thought of as things like, oh, at test time, my self-driving car hasn't seen anything that it's had during training because it's just a whole new world. But we have time distribution shifts and we have space distribution shifts. Self-supervised learning is this idea usually applied to models like very famously LLMs. We have all this text data on the internet. We can learn from the structures in that text data and then train really quickly when we need to apply that to something new. Well, we have a lot of data on the internet, right? We have a lot of text. We have so much more satellite data just in terms of volumes than there is text on the internet. And all of these are then places where these are threads where the machine learning community is already fundamentally working on this technology, but we're not working on it with the angle of satellite data or ecological data. And we have the opportunity to really do that. And part of that is, I think right now, really about translating what the core challenges are. So that's why we, as a subset of machine learning people working on geospatial data, tried to start that conversation. And then I think that you'll probably read that paper and say there's 1,000 things we missed. And that's where we start having this conversation. Yes.
Build off what you were saying earlier about uncertainty. So like, and what I was saying about bunny sensors. I'm doing speech distribution modeling. That's why I'm here. And so like, I think the bunny sensor is people like, you know, these presence absent or presence only data sets like GBIF, things like that. And they'll have things like, you know, when things were observed, like going back to what I was saying, like temporal, like when was the observation made, all that stuff. So you'll have like basically a CSV with a bunch of labels. Those labels might be species and time, could be other metadata as well. I know not doing a machine learning approach, there's a big not controversy, like a big thing they think a lot about in that space is the uncertainty of using presence only data. You don't know where things aren't.
Yeah.
How do these kind of machine learning approaches deal with the fact that you know where you sampled, you're not even sure you maybe got a complete sampling of that area. So like your
Yeah.
uncertainty of where things aren't is very high.
Yeah. Yeah, it's an interesting question, and there is a kind of small subfield of machine learning led by a couple of key researchers that look at those questions in particular. So species distribution modeling is a big example there. And the kind of keyword there would be presence only priors for me. That's a paper that actually models this pretty explicitly, not unlike the earlier example there, but using a prior to describe, okay, I have this sequence of observations, but what should that actually tell me about the ground conditions? So I think that's a really interesting research space where the data has a structure that you know that they do, and there's kind of older school than machine learning ways to model that, right? Yeah. So finding that integration and understanding where machine learning can push what's been done already, super interesting.
Yeah, awesome, thank you.
Yeah.
We have a few questions online. So if Elsa, you want to go first?
Sure. Can you all hear me?
Yeah.
Where you're
Okay,
from.
great. I guess I kind of have maybe more of a comment and then also a question. My comment is that we've done some work around the land cover models, and one of the things that's challenging about is that NLC data from the USGS isn't actually observations. It's like another model that was trained on satellite data already, and so we get like really unrealistic performance out of those models, and it's like unclear if it's actually doing anything. So I guess I am a little bit curious about like what your experience is with that and how to kind of get around that issue.
Yeah, that is a wonderful point, Elsa. Yeah, okay, wonderful point, Elsa. And yes, again, this is kind of the motivation. This data, even at 30 by 30 meter resolution, might not be trustable as ground truth data that we would call in machine learning. So a lot of details of this work are left out, but when we go to actually evaluate these models, we're evaluating them on a different 1 by 1 meter land cover data set called Enviro Atlas that, again, people have annotated from imagery, so it's not perfect. But that helps us a little bit on the evaluation side of things.
Mm-hmm.
Did you have a second question in there as well? Looking around to figure out the characters.
I did, and I guess this is a little bit more food for thought, that like one of the things that that I think is challenging about like merging earth sciences and machine learning is that there is a lot of like theoretical knowledge about how things work and like about what spectral signatures we might see from different types of objects and all of that kind of stuff, as well as a great deal of expert knowledge, especially with some of the partners that we work with in indigenous communities. And so I'm curious if you see ways that kind of knowledge can be incorporated into the machine learning effectively.
Yeah, that's a great question. And you have really well summarized one of the things that I think is most exciting about this space, which is kind of taking away what computer scientists are often obsessed with, which is this notion of abstraction, right? A general model that's going to solve everything. We've abstracted the problem into this learning framework, and I'll tell you why it's great. And I just did, right? Because I'm a computer scientist. But at the same time that I'm working to get these general-ish frameworks that can incorporate different situations you might face with data, it is really important that when we're doing individual research projects that aren't meant to be methods in machine learning, but are meant to be interdisciplinary, that we're having those conversations around the structures in data and the structures in physical processes and incorporating that into our modeling. And I'm really excited about that as a way to make models more interpretable, more accurate, and of course, more efficient. Because if you can encode prior beliefs or constraints on what your model should look like, the parameter space of what you need to learn hopefully goes down. But right now, there's no general abstracted formulaic way of doing that type of research, which is why, to me, it's such an exciting space to innovate in.
Thanks so much.
Yeah, thanks for your questions. Yes.
My question is related to Jennifer and Robson's, and in my research, I mainly use secondary data and outcomes from machine learning would be great opportunities to improve or enhance the new research for me. And in your slides, you use R square to check your model accuracy, but I'm wondering if there are any other indicators or estimates to persuade other scientific communities that your data outcomes are reliable.
Yeah, great question. So I'm a big believer in, if you're going to use the model for an application, it's not machine learning, you got to ask the other people on the team what the right metric is. So part of this is because in machine learning, when we're training models, we need the loss functions that we're optimizing for to generally be differentiable so that we can actually do the optimization process. That's different from evaluating whether models are performing well in practice. So in this talk, we looked at R squared for mosaics, and that's actually because it's a number between 0 and 1 where you can put all of these 7 different target variable distributions on one scale that makes sense. We also looked at, in the poverty prediction example, Spearman's correlation to understand, are we generally ranking people the right way or ranking places the right way, because that's closer to how we're going to use this model. But I think the question of what comes in, what's the right metric? So when we're looking for discrete events over space, like my current project, I'm trying to find artisanal mining, we're looking there at things that are closer to area under the ROC curve, things that trade off precision and recall when we're looking for discrete events. And so these are all, again, things that the machine learning community takes as evaluation metrics, but part of that conversation is understanding, hey, what types of performance do we actually need from this model? And that's, again, one of these things that has to be a conversation between everyone on the team. Yeah, great question.
Yeah, we share more online, but we're a little bit over time.
Okay.
So up to you if you want to stay.
Yeah, I can answer them quickly if they can be answered quickly.
Okay, if you want to unmute and ask your question.
You can go first.
Hey, Esther, this is Guofeng Chao from Geography Department. I think we met when you came in for the interview in early last year.
Awesome.
It's a great talk. So I think that you're talking about the challenges, like the way geographer and jazz scientists are wrestling for years, spatial autocorrelation, heterogeneity, uncertainty stuff. I think it's not a really question, probably it's more comment. So it's related to the previous question, actually. So, how to do this sort of accuracy assessment, considering the spatial autocorrelation stuff. I think this is a very important topic and an important problem to be addressed. For example, you're using R square, to evaluating your mosaic features. I think that the challenge probably going to be, it's kind of hard to summarize all this accuracy statistics using one numbers, right? So the plot is showing that for the whole United States, it just came out one R square. So by doing that, it kind of lost lots of information in that, right? So this there's definitely an interesting topic to be continually research on. Not a really question, just some comments.
Yeah, I agree with you, and I'm looking forward to talking with you about that come August or maybe even before. But yes, having one global single metric of performance is not going to cut it, right? We saw that again with the poverty estimation, where if we looked at performance across an entire country, we were way overestimating what might happen if we went to use this model. So that's a clear case where urban and rural divide actually makes a lot of social sense. But for general prediction, where you just know that there's spatial autocorrelation over geographies, what's the right way to capture that is a super interesting question.
Yeah, there's not lots of development in spatial stats literature and ecology literature. There's, probably can be borrowed from the machine learning.
Yeah, that would be awesome. Did we have one more question on Zoom?
Hi, so I'm actually an incoming applied math master student, and I was looking through and I saw your profile, and I came to this talk because I was interested to maybe like participate in like maybe a summer research or something like that. But I just want to know, like, I came from machine learning, and my undergrad degree is also in math, and I came from a machine learning background, and I'm wondering, like, where should people like us start? Because I I don't have a lot of environmental science or geospatial science background. So I think I lack skills in that aspect, and I'm just wondering, like, what would you suggest to how to start coming from that background, and what advantage should I also maximize with this kind of background? Thank you.
Yeah, that's a great question. I too came into my grad degree with basically a computer science and statistics background. And I found my way to this research agenda because I mean, I care about the natural world, right? I love being outside. I think that we need to act now. But at the end of the day, there are really interesting math questions here. And those two things together are what keep me really excited about this space. And so I would say, yes, I'm excited that you're excited. In terms of what are the opportunities out there, that's something that I'm hoping to start a conversation with talks like this and with kind of cross collaboration. So I might even punt that question to Jennifer.
Keep coming to this seminar series. And we're hosting a summit in May here in Boulder. Big data for environmental resilience and adaptation. That might be a good forum, but we should probably close out. But I think this is the longest one of these seminars has ever run. And I think it speaks, no, I was gonna say, I think it speaks to the interest and enthusiasm about your work. And we're so excited you're coming. And please help us build those bridges and connection points. And there's a lot of interest in the biodiversity piece that you kind of hinted at. I would love for our community to talk to you about JEDI data and biodiversity data and all of the good things. So let's just keep the conversation going.
Awesome.
Yeah.
Thanks, everyone. Thank you.
Thank you.